Sure. Okay, so I have one last matter. Is there anybody here who would? So we are going to live stream the event and then post the recordings afterwards. Is there anybody here who would prefer that we not do that? Because if anyone would prefer us not to, then we won't. Going once, twice. Okay, thank you.
Is that coming through? Can you hear it? Yep, good. Okay, well, I'm honoured to be invited to speak at PLMW. I'm going to tell you a bit about some work I've been interested in, I guess, for the last 7 or 8 years, what I call effect handler oriented programming. And as it says there, I currently work at the University of Edinburgh, but I'm paid by the Imperial College London. Before I go into the main topic of the talk, I'm going to show another slide. This is a bit of a digression, but I like to show this in all my talks now because I think it looks quite pretty. My former PhD student, Simon Fowler, made a poster of for this programming language Lynx that I've been, I guess, the lead developer of for the last 13 years or so. So, yeah, Lynx is a functional programming language for the web, conceived by Phil Wadler, who, if you haven't met already, I'm sure you will come across him. And yeah, he invited me to start working on it when he started up this project. And probably this is something that's maybe worth bearing in mind if you're thinking about doing research. I remember he had a really strong sales pitch saying, we're going to make this new programming language, it's going to take over the world. That's the way you get funding. But I remember having a conversation with one of his PhD students, Ezra over here. He was rather disgruntled when he realized that wasn't actually the aim. And when we're building research languages, often what we're using them as a vehicle for trying out ideas and doing research. And I would say that Lynx has actually been very successful in that regard. We've produced quite a lot of papers, we've done lots of interesting research. And then that research transfers, hopefully, into practice. So yeah, here are some of the sort of active areas that we've been working on. So Lynx, the sort of main selling point of Lynx is you write your code in a single language, and then that gets translated to the different tiers of the web. So it will generate database queries for you, it will generate JavaScript, and so on. And these people here and here are the sort of core developers of Lynx over the years. I'm not going to really go through any of these in any more detail. I just wanted to highlight, I suppose, this area, concurrency and distribution, is one of the other main thing I've been working on over the last few years. So adding session typing to Lynx. But there's lots and lots of other features. And effect handlers, that's the topic I'm going to be talking about now. We've implemented this abstraction on top of Lynx. Okay, anyway, onto the main talk. Effect handler oriented programming. So, as theorists or as functional programmers, there's a nice idealized view of computation where we just view a program as a black box. It just takes inputs to outputs. And that has all kinds of advantages for reasoning. You know that some things can't just change underneath you. But even as functional programmers, we do need to write programs that interact with their environment. And this kind of interaction we call effects. And effects are everywhere. We have all of these kinds of things: I/O, concurrency, distribution exceptions, choice, etc. However, in typical programming languages, each of these things is ad hoc and built in, and often you have similar kinds of features that just get re-implemented over and over again. So a particular case in point is JavaScript with web applications and concurrency. There's a whole range of different abstractions that JavaScript has sort of gradually added that do fairly similar things. So things like generators and iterators and promises and async await. So it's a bit annoying that there's all this duplication, and there's a maintenance cost to this. So effect handlers are a particular abstraction that generalizes all of these things. They were originally introduced by my colleagues Gordon and Mattia in a very theoretical setting, building on the theory of algebraic effects. Crucially, they are composable, and they allow you to define effects in a user-defined way. And they kind of give you direct access to the environment. So if you know about some of these things, resumable exceptions, monads, and delimited control, it's very much the same kind of idea. So you get access to the continuation. Where I guess effect handlers win out over some of the previous abstractions is that they have nicer composability and modularity properties. There's also actually quite a bit of interest in industry in using ideas from effect handlers. So for instance, the JavaScript React library, the core of that, the implementation is directly inspired by an efficient implementation of effect handlers in the multi-core Camel programming language. And Uber's Pyro language actually builds in effect handlers for abstracting over different forms of statistical inference. All right. So I'm going to spend most of the rest of the talk actually just going through some simple examples to try and get across the idea of what effect handlers are and effect handler-oriented programming is. This is maybe a somewhat contrived example, but I think it's quite simple, so I like to start off with it. So the main idea is when we're programming with effect handlers, we start off with a signature of operations that our effect is allowed to do. So here I'm considering choice and failure, so I have an operation choose, which will return a Boolean, and then an operation fail, you can think of that as like an exception, which if it were to return a value, it could return a value of any type, but which is rather equivalent to saying it can never return a value, because how could you have a value that has every type? And then, given these operations, we can write programs over them without actually, before we define the meaning of the operations. And then having written this computation, the effect handlers are the way of defining an interpretation of that. So what's going on here, I have I'm tossing a coin. I'm going to make a choice and either return heads or tails. That's all a toss does. And then the idea here is we have a drunk who is trying to toss a coin, and they may drop the coin. So first we decide whether the drunk catches the coin, and then decide whether it's heads or tails. And if it's dropped, then we just fail and return no value. And then we might repeat that several times and return a list of tosses. So here's a first example of a handler, but this is just a standard, well, almost standard exception handler. So effect handlers generalize exception handlers, hence the name. I guess the somewhat unusual feature of this is that it's an exception handler that, as well as saying how to handle the exception, so in this case it's just going to return an empty list of results for an exception. You also say what to do if you actually successfully return a value. And in this case, it's going to just return a singleton list. So if I run that on the value 42, then I just get the singleton value 42, and if I run it, if I get an exception, then I get an empty list. So that's a standard thing. But then here's where the new feature that effect handlers introduce comes in. For the choose effect, we get an extra parameter which is called a resumption, and this represents the rest of the program. And choose, if you recall, returns a Boolean. So the resumption is expecting a Boolean. So the idea is when you see choose, you'll substitute in whatever that Boolean value is when it gets invoked here. So this handler, all it's going to do is whenever that you do choose, it's always going to choose true. So it's a biased choice. So if we try to toss a coin, then you'll just get heads. A more interesting handler, which is also using the resumption, but now non-linearly. You get to use it twice. Whenever you make a choice, you get to run the rest of the program once with true, and then again with false. And this is going to allow you to basically explore the entire space of possible results. We could also define other handlers. I mean, you could do one if you had a random number facility. You could randomly choose and do sampling, and then you can build more sophisticated examples. So yeah, so this example, if we toss a coin, we get both heads and tails. And then, is that highlighting visible? Sort of, anyway. So this is where part of the power of effect handlers comes in, is we can compose together these handlers very smoothly. So if we get the drunk to toss a coin twice, and we compose the list fail and all choices handler, then it first of all interprets all of the failure, then it interprets the choices, and then we concatenate all the results together, and it's basically giving us all of the possible successful results. So this is a very simple example, but you can build much larger programs this way, and you can swap in and out different interpretations. Just illustrating here, if you change the order of these things, then it's going to build up the list of all the choices, but when it comes across any possibility of failure, that just causes everything to collapse and you get a single result. Okay, so this is a somewhat contrived example, but it's shown you the three of the different modes of use of handlers. You can not use the resumption, you can use it once, or you can use it multiple times. Here I think is a more compelling use case, where we're going to implement on one slide cooperative concurrency. So I'm going to just have one operation here, yield. It doesn't return, so one is the type that has a single value in it, the unit value. So the idea is you have cooperative threads, and when they're ready to yield to another one, you invoke the yield operation. So here's a couple of example threads. So this one prints A1, then it yields to the other thread and prints A2, and similarly. And now we define another slight refinement of handlers, where we thread a parameter through the handler. But this pretty much gives you a full implementation of concurrent threads. So we've got two cases. I should say, yeah, what the parameter represents is a pool of possible resumptions, i.e. a representation of the current threads. So if you consider the case where there are no threads no resumptions running, if we finish and we get a unit value, then we just return the unit value. If you yield and you're the only thing running, then you just carry on running the resumption. And now the resumption takes the parameter as well, so the list of all the other resumptions, as well as the unit value that yield needs to return because it has the type. And then here it gets more interesting. If If the current thread finishes, then you just take the first one that's waiting to run and run that one. Similarly, if you get a yield, you take the first thread, but crucially, you take the rest of the current thread and you stick that onto the end of the queue of resumptions waiting to run. So in order to make this convenient to use, we need a couple of helper functions, because you probably don't want to be explicitly having to write code that actually threads these resumptions through everything. Instead, we're going to represent a thread just as a function of type that takes a unit value to a unit value. So this helper function co-op with it lifts a thread up to being a resumption. And all it does is it invokes the co-op handler with the parameters that are passed in there. And then this is the interface we're actually going to want to use, which just takes a collection of threads and runs them all. So it just maps co-op with over all of them. And then sure enough, if we run this, it returns a unit value, but it has the side effect of printing out the interleaving that we'd expect. So you go here, and then you yield to this thread, and then that yields back up here, and so on. So that's quite nice. We can now, it now gets a little bit more complicated. So this is a situation where you statically have a collection of threads you want to run, but you can't create new ones. It's natural to want to add another operation, which I'm going to call fork, that allows you to fork a new thread. And the representation of a thread is a function from 1 to 1. So we now have a parameter passed into the operation. This thing here in the square brackets is crucial. So that's an effect type. And that says that the body of that thread, that also needs to be able to fork and yield. So this is actually a recursive signature here. So now, yeah, given this setup, we could, rather than writing two separate threads, we can write a single program that forks them. And we're going to print out some things in the main thread as well. And we don't actually have to make a very big change here. The handling of yield is identical, and the helper functions are identical. We just need to say what to do with fork. I could have been more modular and defined this as a separate handler, but I wanted to put all the code together, so I did it this way. And what this is going to do is, so actually these are both essentially the same cases. When you try to fork, it's going to immediately try and run the thread, and it's going to stick the resumption into the pool of waiting resumptions. So now you get the same interleaving between these two threads. No, actually, sorry, you don't. It's more interesting. Yeah, so what happens? We do M1, then we fork this thread, do A1, it yields back to the main thread, prints M2, and then that's going to fork this thread, it does B1, but when you yield here, now this original thread is at the next one to go, so it actually goes back to there. And then similarly, the main thread now has priority, so it will do that one before going back to there. But of course, you don't have to fix. Oh yeah.
In the effect signature, is there any difference between the two arrows and fork, or just the second one?
Yes. So this is the signature of an operation which takes a parameter and returns a result, and they can't have effects. Whereas this is just a normal type.
Oh, okay.
Because we're actually passing in a function as an argument. Okay. But yeah, so here I've given you a particular scheduling strategy, but another nice thing about handlers is we can just swap in an alternative one. So rather than when you fork immediately running this thread, we carry on running the resumption, and then we stick this one in the pool. and then we get a different interleaving. It's going to just run all of the main thread until it gets to the end, and then it will interleave these two. I'd say, yeah, that to me is yep.
Could you repeat what's the meaning of the CO in bracket?
Oh, that says that the body of this thread is allowed to have the same effects. It's allowed to do yield and fork. You want your threads to be able to continue being concurrent as well. Yeah. So this is nice because you can not only build this, you can build all kinds of other models of concurrency. You can customize it as you like at any level of granularity. So I'm going to briefly go over the operational semantics of handlers. I've not included all the features of the language, but the important ones are what you do with handlers. So if a handler produces a value, then we look at the return clause and we just substitute that value in there, so that's easy. This is where the interesting work happens. If you come across an operation inside a particular evaluation context, well, we substitute the value for the parameter in the clause. But we also need to provide a value for R. And what we do there is we take the evaluation context and turn that into a function, but we wrap that up so that the resumption also gets handled in the same way. So it's rehandled with the same H we started with. And then this is a freshness constraint that makes sure that the closest handler is the one that kicks in. There's a slight modification to that for doing parameterized effect handlers in the obvious way. And as an exercise, you can try and express parameterized handlers as non-parameterized handlers. There's another variation where you don't explicitly handle with the same handler every time. These are called shallow handlers, and these can be quite useful because it allows you to switch to a different kind of handler at different points. It's an interesting exercise to express shallow handlers as deep handlers. Let's see, how much longer have I got? I don't want to...
About 10 minutes.
10 minutes, okay. I will show one more example to illustrate why shallow handlers can be useful. So here we're going to have, rather than handling one computation, we're going to handle two computations simultaneously and think sort of Unix pipes. So we're going to have one computation that's sending messages and another one that's receiving messages. In this case, just natural numbers. So my example is necessarily going to be very simple. The sender is just going to send a sequence of increasing natural numbers, and the receiver is just going to receive one of those. And using shallow handlers, we can define these things as two mutually recursive functions. So the pipe takes a producer function, a consumer function. It runs the consumer, and if it comes across a receive, it switches over to copipe. And copipe does the opposite thing. The important thing is, I guess, if a message gets sent here, then it's passed into the consumer over here. And then if we take this example and we reduce it, we start with the pipe and it turns into a copipe. This is the continuation here, which is there's nothing more to do, it's just the identity. And then you do the sending, and then it receives as a 0. Okay. You can implement pipes using deep handlers directly, but it's kind of tricky. Or you could use the generic implementation of shallow handlers using deep handlers to generate an implementation. Okay. So that's most of my examples done. I'm going to just mention some of the research languages that are under development for doing effect handler-oriented programming. I guess these top three here are actually languages that were specifically designed for the purposes of programming with effect handlers. The other ones have had them added on later. I'm particularly involved in Frank and Lynx. Coca and multi-core OCaml have had quite a lot of engineering effort put into them. Multi-core OCaml in particular is actually very fast if you use your assumptions linearly. But yeah, if you want, you can look those up if you want to find out more about them. Here's some of the things I've worked on in the area of effect handlers. I'm not going to go through these, but if anyone's interested in any of these things, then you can ask me later. So what are the main sort of challenges for making effect handlers actually viable as a programming abstraction in mainstream languages? I'd say that the sort of two main classes of problem we have to address are actually realizing this modularity. The main tool we have there is effect typing, which I haven't really talked about in much detail. And there's lots of different designs and lots of interesting problems that crop up there, and lots of extensions, so there's plenty of scope for new research. The other thing I've alluded to, I guess, is efficiency, and there really it's about developing compilation techniques to make this run fast. There's some very promising results, particularly using segmented stacks in multi-core OCaml. That works very nicely for linear use of the resumptions, which captures the cases like that concurrency case I showed you, but doesn't capture other use cases. So probabilistic programming requires you to use the resumption more than once. Okay. Some new research directions which I'm quite excited about. So most of the work so far has been about using these things as high-level programming abstractions. But I've, over the last couple of years, been talking with Andreas Rosberg, who's the editor of the WebAssembly standard, and they're actually very keen on adding effect handlers as a low-level programming construct. And the advantage there is you don't even need to add this to your programming languages. You get some benefits. You can compile all of these ad hoc high-level abstractions into this single backend and reduce your maintenance cost and hopefully get an efficient implementation. Gradually typed effect handlers is something we started thinking about. So gradual typing allows you to sort of seamlessly transition between a statically typed way of programming and a dynamically typed way of programming. We're hopeful that might make it easier to transition to systems with effect type systems, because adding an effect type system to, I don't know, C or something is not really something that's going to fly immedially. Something that a lot of people have been talking about recently is lexically scoped effect handlers. So the way I presented them is that there's effectively a kind of dynamic binding going on. These operations, their bindings are defined by the handler later on. And lexically scoped effect handlers are a little bit less expressive, but they might offer some improvements. Resources. So this effect handlers bibliography is actually really useful. That's sort of collaboratively maintained, and it has links to all kinds of things. There's a couple of tutorials here. They're more maybe theoretically oriented. Andre Bauer's actually giving a keynote on Wednesday, which brings me on to some relevant talks that are coming up in the ICFP program. So actually all of these have a rather different emphasis to what I've been presented. They're all really focusing on reasoning about effects, But they all have connections to effect handlers. I believe Andre is going to be talking about a theorem prover based on effect handlers called Andromeda. There are also, at other workshops, there are some related things. Although I guess Heidi is concurrent with this workshop, so you're probably not going to be able to go to that one. But these two talks, I think the connection is to do with the effect type systems and interesting questions about binding that come up there. And I believe Connor was, I don't know if he's actually even finished his talk yet. So, and then there's a talk later in the week at the Haskell workshop, which is comparing the expressive power of monad transformers and effect handlers. Okay, I'm going to finish here, I think.
Okay, so do we have any questions for Sam?
Yeah.
So for your effect handlers, you now see some kind of way to represent your effect syntax, so that your effect handlers have something to handle. I have used free monads in the past to do that. Do you have any favorite techniques for your work?
You can absolutely, yeah, I mean, free monads that's the default way of sort of implementing it on top of Haskell or an existing language. You can certainly do that. And it works fine until you try to do the modular composition of these things. And then there are lots and lots of different hacks that you can use on top of existing languages that work to varying degrees. You can use row type systems if you start from scratch. The consensus seemed to be, when we had a discussion about this a few years ago with regard to Haskell, that it would be really nice to add some feature that allows you to have unordered things at the level of types. Because, yeah, you don't want to, with monad transformers, you tend to end up with this sort of serialization of effects, which is very annoying in practice. And there are various encodings that can help with that. Scala, I think, there's an implementation that uses intersection types in an interesting way. But yeah, the work I've been doing has been mainly, I do my own language, I can define something that makes it easier and more concise. So Frank has a rather eccentric, you might say, syntax, but is extremely concise and direct at expressing these kinds of things.
Okay, so we have a couple questions from Slido. So is handling with a composite handler the same as handling nesting two handlers?
That was what I meant, yes.
Okay.
So in fact, handlers are not closed under composition. So I really meant turn the handler into a function and then...
Instead of using a parameterized handler to keep track of the list of resumptions, could one use primitive mutable state?
Yes.
And can one always do so?
Yes. You have to be careful because you have to be careful about aliasing if you actually use mutable state. The other thing you can do, which is quite fun, is you can actually implement an effect for managing the queue of resources. So you might have an operation for adding something for queuing and dequeuing. And then you don't even need the parameterized thing, and you just compose several handlers together. And we have a nice example of that we've done in Frank, where we've built actors by composing 3 or 4 handlers.
Any other questions?
There's one here.
In your effect signature for concurrency away with this fork, so you said this is a recursive effect signature. Is that any trouble in general having recursive effect signatures? Is your language still
well, there is no, it isn't.
Okay, you can do whatever recursion you want.
Yeah. No, and indeed, so in F and multi-core camel, which didn't have effect type systems, I remember people implementing this funny example where it seemed like, you could write recursive code, but then and it looked like you weren't doing anything dangerous. And the way that you see why you were able to write that code is by observing, well, if you have an effect type system, then it has to be recursive. Well, you could probably have a restriction on your recursive types to make sure that they're positive or strictly positive, so you're only allowed the recursive occurrences in certain places, and then you might end up with something that still terminates.
That already rules out your example, right?
Yes.
You're saying because it
Oh, I see. Yeah, no, there are other ways of doing that, and there are other more interesting recursion schemes you can do. So there's work by Nicholas Wu and various other people who should be around this week on scoped effects, which specifically addresses this kind of example.
I have one more question about the code in bracket. Is it annotating the function type, or is it annotating the one type? And can I put the tuple instead of one?
You can think in a traditional effect system, you often write the effects on the arrow. You can think of it as being on the arrow. I just wrote it there. It's more like this kind of Haskell monadic notation, where you write it on kind of the right of the arrow. But it's the effects that happen when you run the function. So if you run a function, it will return a value, and it will also potentially do some effects.
Okay, let's thank Sam once again.